Right. Happy Wednesday, everyone. Our webinar has just begun. It seems that everywhere I turn, there are people here ready to learn. The sun is out, the weather's fine. That has inspired me to rhyme. Why would I do that, you say? Is this an unnecessary delay? To that, my reply is, hey, relax. Let's take your poet to work day. Thanks to improvements in plumbing fixtures and codes, the design of typical residential water distribution systems has not kept pace with reduced water consumption in buildings. Consequently, many residential systems are oversized, and oversizing a domestic water system increases energy use, water waste, and the embodied energy and carbon of the plumbing system. Today, we're going to look at an alternative design methodology that results in a domestic water system appropriately sized for the population it serves, and that reduces both first cost and operating costs. With us today is the one and only Gary Klein. Since the early 90s, his effort to incorporate hot water as a system into the core principles of building science. He spent 19 years with the California Energy Commission, and Gary is all about right-sizing premise plumbing and water heating systems. His work was recognized by IAPMO in 2014 when he received their Green Professional of the Year Award, and the very next year, the Department of Energy awarded him the Jeffrey A. Johnson Award for Excellence in the Advancement of Building Energy Codes. Now I need to make sure I mention our sponsors for this webinar. The first one is Mitsubishi Electric. Mitsubishi Electric promotes sustainable building through the electrification of residential and commercial heating and cooling products. Their mission is to advance technologies that reduce waste output, promote sustainable resource cycles, while increasing energy efficiency and eliminating dependence on fossil fuels. Next, we have Panasonic Healthy Indoor Living Solutions. Panasonic is helping builders across the country differentiate themselves with powerful, code-compliant, and cost-effective indoor air quality solutions that provide a safer environment for homebuyers. Then we have Huber Engineered Woods. Fueled by on-the-job site analysis and building science principles, Advantech subflooring, Zip System building enclosure, and Exicor product solutions have changed the way construction teams build quiet floors and air and watertight building enclosures. Learn about their new Exicor line of magnesium oxide panels at www.huberwood.com. Finally, we'll soon be welcoming a new sponsor to the Housing 2.0 program, Schneider Electric. Look for more information from them soon. Now, here at Green Builder Media, we welcome your questions. All we ask is that you use the questions box on the right side of your screen to send in your questions. I'll review those and pose them to Gary during the Q&A time set aside after his presentation, unless you have a clarifying question. And if so, we'll try to get to that right away. Now, Gary asked that a couple familiar faces join him at different intervals throughout his presentation today. So here to join Gary and I is Sam Rashkin.
Hey, thank you, Mike. And I always like to get away from the conventional bios when I introduce these thought leader series speakers. And today is one of my good friends, Gary Klein. Gary and I know each other way too long. And I have to say, I love the way Gary just makes a topic such as water heating so fascinating. So you're in for a great conversation today. But more importantly, what I want to really emphasize is most of you are tracking the Housing 2.0 program. We're really working to make high performance builders the industry leaders. And we do that by taking them on a path to becoming user experience leaders. As we know in virtually every other industry, user experience leaders are 3 times more resilient and return 3 times more profit to investors. So getting on that user experience leadership path is really important. And Gary is the best I know when it comes to how to optimize everything about water, water heating, plumbing. And so it may be something that's not on everyone's top of mind, but it is so much opportunity here. And with the Thought Leader series, we really like to take deep dives into real good details that are great opportunities. So you're in for a treat today. Gary's one of my favorite speakers, and I hope you enjoy his content.
I guess that's my cue, right?
Let's say it's your cue.
All right, good. Thanks, Sam. You know, I would observe that the fact we've known each other a long time is a good sign. It means we all got old. It's a good deal. Let's move on. I want to share with you what we've learned over the last few years related to water system sizing in particular as it relates to hot water, but it's also applicable to cold water. And let's just get started. So what are we aiming for? I don't think if we know where we're aiming, it's hard to know if we arrived. And I've interviewed over 50,000 people in the last 30 years looking at hot water as a system. And what I have learned is that people want things to feel right. They want their toilets to flush first time every time. They want clean clothes, dishes, and bodies. And for hot water, they want the service of hot water as efficiently as possible. Now, this is really weird. I used to work at an energy commission, the one in California, and they're all about efficiency, but it doesn't make sense to discuss efficiency until the desired service has been provided. If we don't provide the service, customers will do their best to get their service. Efficiency be darned. So how big is hot water? Well, water heating is the first or second largest single family residential portion of the energy pie. It's 15 to 30% of a house's total energy use. It's even larger percentages in multifamily because there's fewer exposed walls and more people per square foot. And as Sam said, while we've made great improvements in all sorts of things in our buildings, we've done virtually nothing to improve the efficiency of water heating. Oh yeah, we've got tankless gas water heaters or high performance gas condensing water heaters. We've now got heat pump water heaters, but we've not looked at hot water as a system like we look at the building as a system, all the other components. Hot water is a system. We need to look at it in the same way as the building science of it needs to happen. So many of you know the work I've been involved in for the last 25 plus years to look at time to tap, reducing it, making it shorter so people don't wait as long to get hot water. And we analyzed that in a project we did for the California Energy Commission a few years ago now. And what we found is that if you can collapse or compact or cluster the wet rooms closer together and close to the water heater that serves them, you can save $1,000 to $2,000 per single family dwelling just by focusing on the spatial differentiation between the fixtures and the water heater that serves them. That decision is made by an architect. Where do things go? And so the architects are unintentionally driving up the cost of construction by virtue of where they decide it's good to put things. We have to have that conversation more frequently and more often about getting the infrastructural capabilities of the building to be efficient. And oh, by the way, have a great house. Well, you have to have a great house. That's the service of house, right? But we found ways to do that. By the way, most of that savings comes not from the material costs, but it comes from labor savings. It's about a week less work on the job site to do this. It's a big deal. So the question that we have to ask as we get started in all of this is, how long should we wait for hot water to arrive? What you see here is a table that's analyzed based on the excerpt from the ASPE manual, the water heating design manual, and they say acceptable performance for hot water arrival is under 10 seconds. So everything in green is under 10 seconds. And I use 1 gallon per minute for my sizing for time to tap, my calculations. Why? Some fixtures are higher now. They're 2.5 gallons per minute, but everything is trending toward 1 gallon per minute at the hot side. Now, some of you are already putting in programs with lead and lead faucets for public lavatories as an example. And some of you are putting in 3/8 of a gallon a minute or a half a gallon a minute for those fixtures, those sinks. And if you're doing those, I use my design work at 1/4 gallon per minute numbers. All right, so if you want hot water to arrive within 8 seconds, you can't have more than 8 ounces of water in the pipe. That's not very much. Sam, how tall are you? Mike?
5'7".
I'm 5'10", Mike? Mike disappeared.
Mike stays on mute.
Sorry, I'm 6'5", Gary.
Thank you. That helps a lot because we needed you in the room. So it turns out that we're all about the height of 1 cup of water, 8 ounces of water in half-inch plumbing. 5'2" or so for half-inch copper, 6'6" or 7" for half-inch plastic pipe, PEX and CPVC. But if you want hot water to reach your fixture, and by hot I mean 105 or more, you have to have no more than 8 ounces in the pipe. It's not far. If you want to use 3/8 tubing and your code allows it, then you can roughly double the distance and still have hot water arrive within 8 seconds. It's not easy to build to it, particularly if you don't have a thing called basements or crawl spaces. And it turns out that over 60% of all new construction, residential construction, does not have basements, has slab on grade, doesn't have crawl spaces, has slab on grade. And because of that, the first floor tends to be plumbed from above, not from below. And it's hard to get there. So you measure time to tap. We've done it in laboratories and we do it in the field. We use this fancy little thermometer. And what you find is when you turn on the tap, the temperature doesn't do much at all for a while. And then it starts to climb. And then it reaches your 100, 105, okay? And so it starts to climb at around 10 seconds into the experiment. And it doesn't reach 105 until almost 18 seconds into the experiment. 1.5 times the volume that's in the pipe. And that's what you find, 1.5 to 2.5. I'm proposing we use 2 for the engineering. The other thing about performance is that you want the showers to feel right, correct? Same with the faucets, right? And so we've got rules that are written that say you can't have more than 2.5 gallons per minute at 80 PSI for showers. I've picked a 2 gallon per minute shower head just as an example. And if you do that, the rule follows the gray line. So when you only have 40 PSI, you end up with 0.7 of what you had at 80. And when you only have 20, you end up with 0.7 of that, or half of what you started with. If you didn't like 2 gallons a minute, you're not going to like 1 gallon a minute at all. But if you specify a pressure compensating flow regulator for your shower head, you will follow the green line, which is a much higher flow rate over the same range of available operating pressures. This 20 to 40 PSI, 20 to 60 PSI is really common in buildings. Maximum the plumbing codes allow in now are 80 PSI into your building. And so most of us are down in here somewhere. And I don't want to be on the gray line. I'd rather be on the green line. Well, for faucets, there's another choice available. You can follow the gold line. And so if you look over here on the right, you can see these 3 aerators down on the lower right do not have any O-rings in them. These are fixed orifice aerators. These are the same flow rates, but they have fixed orifice. So they're going to follow the green line instead of the gray line. Okay? These are also single core pressure compensating orifices, the green line. But this one here is a 1.2 gallon per minute faucet aerator, and it's following the gold line. They're starting to make dual core in more flow rates, but right now they're available for sure in 1.2, which for lavatory faucets is great. I want to be on the green or gold lines. I want performance. So do customers. If you sell them a 2.0, they're getting a 2.0. Okay? If you sell them a 2.0 fixed orifice, they're getting whatever the pressure gives them. And they may not be very happy, and then you get a call. Oh boy. Let's think about this for a minute. Isn't the goal to deliver hot water to a tenant in every apartment or the people at their faucets in their house? That's the goal, right? And so when we waste energy delivering it to the consumer, that's not part of the goal. That's sort of what you have to put up with because the water heater is far from the fixture. Well, in multifamily apartment buildings, water heaters are often in a mechanical room, which is, in diagonally opposite corner of the building from the furthest fixtures up on the 3rd or 4th floor. And you end up with a large run of pipe to connect A to B. We analyzed a building last year that we did the design for, a new building of the same type and size. And we went in and we measured the hot water that was used, and we measured the losses in the circulation loop. And what we found was that the losses were bigger than the uses. In fact, they were 50% bigger than the uses. That just bothered us a whole lot. It shouldn't be that way, right? It should be the losses should be less than the uses. That would make a more efficient system. And so when we looked at the design that we proposed, which I'll talk about a little bit more later, we changed the plumbing design a bit, but we got the losses to be smaller than the uses by a lot. And that is what we're aiming for. It turns out that the original design, which was specified to have insulation by both the code and the building specifications, is acting as though there's no pipe insulation throughout the plumbing, except the mechanical room. I'm sorry, that's not the way it's supposed to work. Doesn't the code say you're supposed to insulate all the hot water pipe? Well, yeah, doesn't always happen. We have to make sure it happens. That's part of the point of all this. All right. So I talked about reducing time to tap, and I talked about getting better performance. Now I want to talk with you about what we've learned by designing the right sizing of the plumbing. The plumbing code rules for sizing were written down by a fellow named Roy Hunter and published in the early 1940s. They were based on patterns of use and flow rates and flush volumes that were true in the early 1940s. Has anything changed in the last 80 years? Yeah, lots. In general, flow rates have gone down and flush volumes have gone down rather dramatically, somewhere between 50 and 90%. And so, but the pipe sizing rules have never changed. They should. And so I'm going to show you how we got to a $5,000 savings for a 92 unit apartment building. $54 per apartment is a lot of money. It adds up. Okay. We also built some buildings, and I'll show you those too. So this is Meadow Senior Living Phase 1. It's in upstate New York. Building E is the one we have lots of measurements on. We've gone in with strap-on ultrasonic flow meters and temperature sensors, and we've been measuring the hot systems a lot in that building. We've been measuring cold water flow rates too, just to make sure we're right sizing both hot and cold. And this is Phase 2. And in Phase 2, we were invited to the project after they'd started the foundations, which means there are no architectural changes that can be easily made, if any. And so we couldn't fix time to tap, which is things that happen in the apartment. We could only live with what we were given. Okay, and we did. This is another building in upstate New York, closer to Albany. And this is a series of buildings, and my colleague Pete Skinner has been doing the measurements for us in upstate New York, and is designing the hot water systems in these buildings. You'll notice solar thermal on the roofs and PV on the parking lots. These are 24 unit apartment buildings. So now, Sam and Mike, I have a question for the two of you. I have a 24 unit apartment building and I have a 35 unit apartment building, both of them in the same climate zone in upstate New York. How many gallons per minute do you think the apartments will use in total? Or you can give me a gallons per minute per apartment at peak. When everything is happening, people are getting up to go to work. If they do that again these days, everybody's getting up to go to work and school, or they're coming home in the evening, preparing dinner, getting ready for bed. Those are the typical peak periods. What do you think the peak hot water flow rate would be?
Just hot water?
Yes, please. You can give me any number you want. I'll convert it.
Per apartment, I'll say 2 gallons a minute.
So you'd say that the peak during the building would be 48. Is that right? Or
Correct.
70? Sam?
Yeah, 48 for a 24 apartment building, yeah.
Yeah,
Okay.
like you said, Gary, there are more people per unit in a multifamily building. So let me go with 5 gallons per minute, which is about 120.
Okay. Hold your horses. I'm going to show you what we found. The plumbing code is the red line. The dark blue line is the ASHRAE modifications that came out in the 80s. The plumbing code line came out in the 40s. This came out in the 80s. This is the water demand calculator that we used to design the 35 unit apartment building. And the newest version is this teal line at the bottom. These are the measured flow rates down here. I'd say they have very little relationship to the code line, off by a factor of 10-ish.
Right. Not even the same universe.
Practically not. They're certainly not in the same game. And that's the point of this exercise. These numbers are small. The measured peak flow rates are small, very small relative to the code required sizing rules. Okay? And even if we took the absolute maximum, not the 99th percentile, it's up here. It's still below the teal line. That's
So the
very,
piping's
very different.
oversized, right?
I'm sorry, Sam?
So the piping's oversized, right?
Yes, rather dramatically. That's the point. All right, so let's keep moving. So this is showing you a graph of how we got the peak flow rates measured. And this is the 99th percentile. Hot is 2.85. The absolute peak we measured was here at about 3.5. This is the 99th percentile for for cold water at 4.5, and the absolute peak that we measured was about 8. Notice that 50% of the flows are way less than a gallon a minute, right? But we size for this number, but the number we pick is way off the screen. It's not even close to this game. All right, so that's for the 35 unit apartment building, Meadow Z. This is a building in Solara. This has got more bathrooms and sort of like it's got more people than the senior housing has too. And so and every apartment has its own, has tub shower combos and its own washing machine. So you'd expect the peaks to be bigger. The 35 unit apartment building only has 3 washing machines for the whole building, 1 on each floor, and only showers, no tubs. So you can't have as big a peak if the flow rates start out lower. But we still see it's only 4 to 5 gallons a minute. It's not that big a number. This tail out here is, almost 9 for the cold water. The hot water tail is only up to 6, same as the last building, not much. Okay, so my friend Pete had an epiphany. If the flows are so low, why are the pipes so big? Seems like a really good question, right? I don't know. Why? Well, there's rules for designing hot water systems or water systems, right? You figure out what you're starting with, you establish a piping layout, you estimate your peak flow rates, which ultimately determines the water service sizing, and then you use the same information to figure out your peak hot water demands, estimate the pipe size, calculate pressure drops, iterate a bit, and which method do you use to do this? There's not just one method in the engineering world. This is the basic process, but there's lots of possible sizing rules. Well, depends where you live. If you live in an ICC state, you'll tend to use the IPC or IRC for plumbing design. You might follow some stretch codes. There might be local adoptions that are different. If you're Wisconsin, you have your own plumbing code. Okay, if you live in other states that follow the uniform plumbing code, that will be your base. There is something new, which is the UPC Appendix M, the water demand calculator. Some people follow ASHRAE, some people follow ASFE, and some people follow whatever seems good that day. And so it's a mess. We really have to figure out how to make it better. This is 2 screenshots of this version 1 calculator and the version 2 calculator. You'll notice that there's an option here. You can't see it, but there's an option here where it says single family residence. You can toggle for multifamily, and it gives you answers over here on the right after you press run. You pick the number of fixtures that you want to count, the number of fixtures, you put the flow rates in for the fixtures you want to use, and you press go, and you get an answer. Here's the link to the water demand calculator. It's also available as an app for your phone. You can do your house on your phone. Multifamily buildings need to use the computer version. So we did this. This is an example for a building that we did the modeling for in Seattle. 92 units, 1 bath per apartment, 12 washing machines in the building. And we compared the exact same structure of plumbing, apples to apples, feet to feet. And we came up with, using the water demand calculator, we got rid of everything bigger than 1 inch inside the building. The big pipe's gone. That's where the big heat losses are, in the big pipe. And we saved about $5,000. The buildings we did in upstate New York, where we actually have real numbers in a change order calculation, we saved over $5,000 in that plumbing too, 35-unit apartment building. Okay, real cost, real change. And that's effectively for all of the piping. But notice that this is just the piping. This is not everything else that's attached to the piping. So you get to right size everything else. And that's another $5,000 estimated per for the building, $54 for the apartment. What's everything else? Well, the mechanical room has lots of things in it. It has backflow preventers and pressure reducers. It's got pumps. It's got valves. It's got lots of fittings. When you go back through the system, the fittings weren't counted in the original example, nor were the pipe insulation. So when you go to smaller diameter pipe, you have the same length, but you buy smaller inside diameter, so the cost is less. Takes a bit less labor to install all of that stuff, and we counted that in here too. All right, now you get to do something with the water heater, okay? We estimated $30,000 for this example, but we have numbers for the project we did in upstate New York, and I'll explain in just a second what we found. How can we right size the water heater? Well, remember the code predicts peak flow rates for hot and cold in total, right? And our numbers are way, way, way smaller than that. So this is the process for the water heater sizing. And the right sizing of the water heater started out with the plumbing code at the building in Seattle at about 105 gallons a minute. Version 2 of the water demand calculator said it's only 11 gallons per minute for that same building. So I could have a water heater in principle that has a heat rate that's almost 10 times less. That's a big difference. The ones we built in upstate New York, we got a factor of 4 reduction for the calculator size we were using, version 1 of the calculator, and that saved us in change order costs $20,000. That's a lot of money, okay? So when you get to right size the water meter. This is so bizarre, it keeps getting better. It's wonderful. This is looking at Seattle. If you're building in Seattle, going from a 3-inch meter to a 1-inch meter saves you about $16,000. Just outside in Skagit PUD, it goes down by, you get to save almost $70,000. So that's $170 to $700 per apartment, first cost reductions. Oh, and then because you have a smaller meter, you get to save ongoing monthly savings because your basic meter charge, the monthly meter charge, just to have it there, the base case goes down. Saves $100 to $250. So this does not account for the energy savings or the water savings that we will actually get when you build the building. So this is the summary of all of those things. It's $600 to $1,200 per apartment in first cost savings. You'll have happier tenants if you can figure out how to lay out the apartments more efficiently and use smaller diameter pipe. Hot water will arrive sooner. And then you get ongoing operational savings that don't include the energy and the sewer, because it's real hard to know where the energy and sewer costs are going to be exactly. How much will you save? The net effect in energy is that the pipe size reductions you get to account for on the hot water system cut the diameter of the pipe down by 1 pipe size on average for the whole building. It's not specifically true in any given segment, but on average, you cut the volume at least in half. That means the energy cost to keep the loop warm go down about by half, not exactly. And the energy lost after you turn off the tap and the pipes cool down goes down by half. Sewer costs you get savings for because you don't run as much water down the drain while waiting for hot water to arrive for 2 reasons. You fix the layout in the apartment and you right size the pipe in the apartment. And that will, again, give you some water savings related to energy savings. And that's how you get the other numbers. And whatever doesn't run down the drain, you don't have to pay for in sewer costs.
So Gary,
so there's additional, yes, sir.
So if you submit a set of plans with all these right sizing solutions, how hard is it to get through the building department?
Can we hold that for just a couple of minutes? We're almost at the Q&A. It's a great question. Hold that thought. So it turns out in order to get the savings, you have to build buildings as they're designed. One of the projects we went and looked at, the sheetrocker was moving ahead of the pipe insulator. And the people doing the construction management weren't stopping work to make sure it went in the right order. If your design says you need to do it, you need to do it because you're expecting performance based on the design. If the design isn't implemented, you have no idea what's actually going to happen. And so I think that commissioning begins with the design and it, all the way through, and then it should continue for the life of the building. We're putting in fairly complex water heating systems in multifamily buildings. Certainly the central ones are complex, and the people maintaining them are not trained in their maintenance. And it's getting worse, not better, as time goes on, okay? And so I think we need to have eyes on systems 24/7. I think the basic strategy needs to be continuous commissioning for complex equipment, in this case, the water heating system. Talk about that more later. Water. We talked about this briefly. Smaller meter reduces monthly fixed charges, and less volume reduces the water waste while waiting for the hot water to arrive. Sewer charges are proportional to the water used. And energy, we talked about this too. The smaller piping means less energy is lost when everything cools down. Okay? All right. Customer satisfaction, it starts with the floor plan. If there's any architects or building owners who are designing new stuff on the call, we've got to work with you to get floor plans such that the fixtures are closer to the sources of hot water. Whether it's in single family or multifamily residential, I don't care. And quite frankly, some of this discussion needs to be in at the schematic design. Once you've made the schematic design, it's really hard to change those walls, change those decisions. We have to be doing our designs for modern pipe and fittings. We need to use up-to-date values to size the piping and minimize the pressure losses. It turns out that the data for friction losses in pipe was also published in the early 1940s by a fellow named Freeman, who was the son of the guy who did the research in 1892. And it's for steel pipe and threaded and flanged fittings. We've never done the same experimental work for sweat copper piping, let alone CPVC or PEX. It's not there. So I decided to set up a lab and start measuring it. And on another call, we could do something related to the details of that. We now have measured data for 1/2 and 3/8 copper, CPVC, and PEX. We have 70 different combinations of pipe and fittings. It's worth looking at to get a sense of what you can do at the end of the system in the apartments, close to the fixtures. We haven't done the work for 3/4 and 1-inch pipe yet, and certainly no one's done bigger than that. The anti-scald shower and tub shower valves, we actually measured those too. And it turns out that, if a company, a Delta or a Moen or a Kohler, any of them has 20 different choices of trim kits, there's one shower valve behind the wall, right? They just change out the trim kits. The expensive piece is the shower valve or the tub shower valve. And so we decided to measure them. Like, it's not part of the standard to tell you what the pressure drop is. And we measured them, and what we found was that the pressure drop varied from a factor of 2 to 1 between the least and the most and the least pressure drop for any given flow rate of shower head or tub filler. And then the last thing is I talked about earlier today. I want you to start specifying pressure independent faucets and shower heads. You can do that today at the time of specification for new construction. It costs you nothing to get a pressure compensating aerator for your faucets or a flow regulator for your shower head. You have to ask for it to make sure you get it, but you can get it, and the marginal cost is 0. All right, time for questions. Sam.
Okay, Gary, I always worry about when I do something new that the building department's going to shut me down. What kind of resistance should people expect if they apply these best practices?
Well, a lot. So we did 3 buildings in upstate New York for a multifamily housing developer last year during COVID. And I'm not a plumbing engineer. My friend Pete is a PE, but not specifically in plumbing. And the firm hired another engineering firm to do all of the mechanical work, including plumbing. And so we had to work with that engineer and explain everything. And at least he was willing to listen and was open to the idea that it's possible. And so he went over our math with a fine-tooth comb. And then what we did is we went to Pete's workshop and we laid out the plumbing for our design, the basic worst case plumbing run on the floor of his workshop, actually out in the parking lot. And we pushed water through it at really high flow rates and measured pressure drop. And guess what? What we predicted would happen in the math was happening in the field. It wasn't built in, 3 stories tall, but it was right compared to what we were looking at in the modeling. So we trusted our model at this point, and we were not having, it was going to work. The plumbing design was going to work. And then our engineer had to talk to the building department, and he said, well, how do I do this? Turns out in the International Plumbing Code, Chapter 6 tells you that water distribution systems shall be designed by a design professional using accepted engineering practice. And accepted engineering practice says you can use any nationally recognized standard for your work. Well, the water demand calculator was first published in the IATMOS We Stand standard for water efficiency back in 2017. So it is published. It is a nationally recognized standard. So he as an engineer can use it as a source for this. It's also in the Uniform Plumbing Code version 2021. It will be in the We Stand 2020 when it gets published soon. And so there's a nationally recognized standard. And then what we did, quite frankly, was we looked at the real measurements in the building as a best case, right? And we compared them back to, let me see if I can go back to the slide here. Not sure when it's going to let me get to the slide. Hold on a minute. There we go. Come on. It's always exciting to try and move through this stuff. Almost. Here. This slide. Yes, this slide. We had the measured data, and this was the design line we were using. So even if you thought that we only measured the certain weeks that got these low numbers, it's still, for this particular building, 5 times less than what the new version of the model predicts. I think a factor of 5 safety is still pretty good, don't you?
Yes, but getting back to my question, how much risk is someone taking on applying these best practices if the building department official expects traditional design and will reject something new and innovative?
They can't summarily reject it. They can push back on it. But we followed the correct practice in the International Plumbing Code. We used accepted engineering standards. Now, could they push back and say you have to do it the other way? Well, I guess that's always a risk. My recommendation is to always bring them along from the beginning. Don't show up at the last minute and say, here. Yeah. I think it's worth explaining. That's been my strategy for years. It's like, let's bring people to the party and explain what we're trying to do, get their issues out before we go too far down the path. And there's always a risk, but I would suggest that the risk of building buildings to the current code increases the likelihood of bad things happening, like pathogen growth in your plumbing systems, because the water's velocity moving through the pipes is so low. So there's an equal risk doing it the old way as opposed to right sizing based on modern flow rates. Then we got more to this question of the pushback. It's possible, Sam, that we just got really lucky with the jurisdiction, but we had to go to the water purveyor too, and they said, well, why aren't you getting a 3-inch meter? We only got a 1 1/4 inch meter for that job. Well, today we'd only ask for a 1-inch meter. And they said, there's no way it's going to have the gallons per minute, all that stuff. Great. Here's what we've measured. Oh, I guess, right? So
But
I
again,
would say
you're armed with all this data. So if I take an average builder and their
uh
architect and designers, and they go to a building department that's expecting a 3-inch pipe coming into the meter, and they want to do a 1 1/4, will they be able to move it through the system and get approved without all the data?
without some backup data behind them, I think they're going to have a lot of trouble to start with. It's still early days. This
So how do
wasn't
we,
published till the first time this was published, Sam, was 2017.
so
It's not that long
what's the
ago.
path to getting to this optimization capability? What's going to take to do it? So what's left to do?
Well, look, how long did it take for, plywood to become a normal product in the building industry? A decade? 2 decades?
Yep.
Right? I mean, so there's a time problem, and we're at the early stages of it. So what Pete and I have done is we've set up a capability to measure peak flow rates. I think we have simple methods for that are available today for anybody who's building buildings that are similar to the type they want to use the demand calculator, water demand calculator in, to actually get pulse counts of the revenue meter and use that to show what their peak flow rates are for the whole building, and show that whatever it is, I don't care where the building is, that the peak flow rate you measure is here and the plumbing code is up here, okay? And what we're going to do is we're going to keep creating a record of here's what we've got, here's our stock, we're building a building that looks just like that one for the same occupancy category, and we think that these numbers up here are way too big. We'd like to use something that still gives us a safety factor of 3 to 4, but for our buildings, which we keep measuring down in here. I think that's the way to go. Now we're going to have to work with the builders, the designers, the engineers, the plumbers. Everybody's got a learning curve here. So to the extent we want to make this happen faster, we have to help with the education, the learning curve, so that people get comfortable with doing this.
So what I would suggest, Gary, is it'd be great for you to lay out which best practices you could do today. There'll be no friction, which have more friction. So by example, we could do the compact plumbing, 0 friction. It's just a matter of architectural design, where we locate the fixtures in proximity to the water heater, we're good. But if we want to use non-traditional plumbing sizes, maybe there's more friction. But with all these suggestions, I think that would be very helpful. And one more side question. I don't know if there's liability concerns, but could you share which shower valves have more and less pressure drop, or at least the ones that have the least pressure drop? Or
so I would rather do that in a session where I'm showing you how we did what we did. We looked at Moens and Kohlers, Deltas, Glacier, probably missing somebody now. We looked at 7 or 8 different shower valves, and they range 2 to 1. And it's really clear why. The hole sizes for the bypass, when you pull the tub spout diverter up, it diverts the water from going down to going back up out the shower head. Well,
yeah.
that hole going back up was 3/16 of an inch in diameter. So no wonder there's a pressure drop problem. Well, those that had a bigger hole had less pressure drop. What a surprise.
Anyway, I was thinking for those that would be interested in seeking out the better valves, if they would know which brands to seek, but I know it could be troubling, and it's just based on a certain set of data. But
I'd like to talk with you about offline how best to do that. I'm happy to share it. I share it with companies one-on-one, but it's not part of a required published standard.
That's why I knew it'd be a tough question. I knew it'd be a tough question.
Yeah, I have the data, and I'm happy to share the data. I'm just not sure I want to do it right now. Okay.
No worries. Hey, Mike, are there any questions that we need to bring in from outside?
Oh yeah, we got lots of questions, but let's get to those again. So Gary, I know you and I have talked about this topic before, but for the benefit of the rest of the audience, you talked about the 99th percentile. Well, what happens when you hit the 1% situation? You know, it's halftime of the Super Bowl, or it's a commercial break during the Oscars, or I don't know what, but what happens when you get into that 1% situation?
Well, that's a really good question. First, it's exceedingly rare. And so Super Bowl Sunday, what did they learn they had to do? Cities knew they had to raise local pressure. For how long? I don't know. They figured out how much time they had to work in advance to raise the system pressure so that there was enough to cover that peak. Okay. Now, we don't get to do that in our houses or apartments. That's not the normal process, right? We live with what the municipality gives us. If we build 3 stories or less, when you go up above that, municipalities sort of expect you to take over the pressurizing of the plumbing in the building. So now you've got your pressure and you've established what it is. So if you're establishing 80 PSI, you have a bit of room to lose pressure in terms of peakiness, right? If you're only establishing a 40 PSI pressure boundary, then you don't have very much to give away. Tub shower valves can lose between 10 and 20 PSI through the valve itself at 2 gallons a minute. That's a big number for pressure drop. And so you have to plan for what you've got carefully. But you asked what happens in that 1%. With standard fixed orifice devices, what we're all used to and what the plumbing codes were written with, if you lose pressure, you lose flow, and you lose it in the ways that we described earlier. Here. It follows this curve, okay? So everything is a fixed orifice unless it's intentionally not a fixed orifice. And when your pressure goes down by half, you get 0.7 of the flow you had at the higher pressure. If it goes down by half again, it goes down 0.7 again. It's the gray line and what you're seeing here. So if we build buildings with the faucets and the shower heads having pressure compensating aerators, and we let the toilets and the washing machines and the dishwashers and the bathtubs remain fixed orifice, when there's a very peaky situation, they will slow down how fast they fill quicker than the showers and the faucets. So the customer will barely notice. Those 99th percentile situations that we've been, and above, that we've done 99.9 as well. Now, above 99 percentile, the events last less than 10 seconds long. So for 10 seconds, you'll see this blip, and then it goes back to being normal again.
Gotcha.
Okay. And so if we build our buildings, as I'm proposing, with pressure compensating faucets and shower heads, then we're going to be on the green or gold lines, and customers won't notice that peak anywhere near as much. That Super Bowl problem, when did that occur? 30, 40 years ago, 50 years ago?
Yeah.
Right? We didn't have pressure compensating devices then. Everything was fixed orifice. And what happened was there wasn't enough pressure for the faucet, everything to flush and flow at the same time. Okay, happens.
So how does this all get skewed if, like, the tenant removes some of those devices, or removes aerators, or removes some of these things?
Why would they remove an aerator?
Why do people do a lot of things, Gary?
Well, no, I think that people remove aerators because they're unhappy with the performance. They're on the gray line. So okay. If you were told your shower head is 2.2 gallons a minute, that meant at 80 PSI. But where you are in your building is only here in the 20 to 40 PSI range. So you're only getting 1 to 1.4 gallons per minute. First, you're upset that you're not getting what you told you were going to get. And second, it's too low to be useful because the shower head was designed to work right at 80 PSI. If you have a pressure compensating aerator in, you're going to be happier with the performance over a much wider range of actual operating pressures. So why will you want to take it out? You were getting what you were told you were given. right?
Yeah.
Will some people take them out? Absolutely. But I think the tendency will be less because the customer is getting more of what they thought they bought, right?
Yeah. Well, let's hit some more questions because we've got some good ones coming in from our audience.
Yep, please.
You had a question about the 92 unit apartment building.
Okay.
Is the loop pipe 1 inch as well?
Let me go to the numbers. I'm pretty sure it is. Sorry, I'm navigating through a device that's being annoyed. This way. 1, 2, 4. Yes, we calculated it, and the maximum pipe size anywhere in the building is 1 inch, hot and cold.
Yeah. Another question that came in from Kendall. How do you account for on-demand water heaters, either centrally located or at the sink?
Great question. So water heaters are either point of source or point of use. Size is not relevant for the moment, but it's either at the beginning of a plumbing system, hot water system, or right next to or near a group of fixtures. Fair enough? And so under a sink is pretty straightforward. If you've got a water heater to serve a single sink, then you bring cold water to that point and let the water heater heat the hot water that's needed for that sink. So your sizing would be a cold water sizing, and the pipe, the supply pipe from the water heater to the sink would be relatively small. Whatever size you need, less than ½ inch, it would work fine for this case. If you have a tankless water heater back in the mechanical room, you have to size for the pressure drop through the tankless water heater at high flow rates. And the pressure drop goes up rather dramatically. I remember looking at the literature for some 199,000 single family residential scale water heaters, tankless water heaters some years ago. And the tables, if you read carefully and far enough deep into the manuals, said that at 5 gallons per minute, the pressure drop through the water heater was 25 PSI. Well, we went out to the field and we measured it, and guess what? We got 27, 25, 26 PSI pressure drop through the water heater. Well, they only had 50 to start with. Now they're in trouble. And they were trying to run 10 gallons a minute through that water heater and wondered why it wasn't working right. Well, it wasn't designed for the right case. It was badly chosen for the application. Putting 2 of them in would have been nice, but the better choice was to put in a bigger, the same size burner attached and condensing, so it was high efficiency, to a storage tank heater. And the pressure drop through storage tank heaters is much, much, much less than it is through a tankless. The plumbing going into the tankless, the water heater has its own issues and has to be sized as part of the system. I hope that answers the question.
Okay.
Sorry, a related thought, Mike. One of the ideas, so there's this idea of distributed water heating, which sort of means 1 per apartment at the extreme, 1 per fixture, right? Could be 1 per bathroom group. Those are the ideas of distributed water heating. But there's the idea of central, which sort of means 1 for the building. But what about water heaters serving clusters of apartments or clusters of wet rooms? And so there's a building in Tim McDonald did last year, the year before in Philadelphia, where there's a 28 unit apartment building. There are 7 apartments per stack, and there's 2 heat pump water heaters at the bottom, literally the bottom of each stack. And so they put the water heater for a cluster of apartments, and that's sort of a shared water heater concept, if you will, as opposed to 1 for all or all for one, somewhere in the middle. And that strategy, I think, is a very, very powerful one for us to look at.
Gotcha.
Okay, new question.
I see, Gary, that you're on slide 21. Can you roll back to slide 14 for a second? Steve had a question about that slide, if the data on that slide was per apartment.
No, that's for all 24, 35, or 40. That's the whole building, central water heating. That's what's so surprising.
Right. Right.
We're not alone, by the way. People in the Northwest have been doing similar measurements, and they end up with numbers on the order of 0.1 gallons per minute per apartment at peak or less. It's very much smaller than anybody would have estimated.
Yeah.
That's
No, you're right. It is
lack of incidental water use or just.
Yeah. So let's move to a different building. Let's talk for a minute. I don't have stuff to show you here, but imagine a hotel. We've, at some time in our past lives, we've been in hotels. Might happen again. And we've been to conference hotels, and we've been to hotels along the freeway on the way to a conference or visiting the relatives or whatever it is. And so the conference hotel has a big kitchen, and they serve meals on plates that require washing afterwards, and they have big dishwashers, and they have lots more laundry than the other kind of hotel does, because in addition to the bedrooms, they have all this linen and other stuff that goes on with the kitchen service. And the hotel along the freeway, they serve breakfast on plastic or paper plates, and you throw away all the stuff, so the washing needs are much less. They only do laundry for the bedrooms. There's not much other linen service going on. And let's imagine that each hotel has 100 rooms. On the peakiest hour of the peakiest day of the year, all hotel rooms are full with more than 2 people. How many showers are operating at the same time? What's your estimate?
20.
Okay.
I bet it's more like 10.
What do you think, Mike?
Well, we've already gone through this before, so I'm not going to answer because we've talked about this before, Gary.
Okay, so Sam picked 20. Most plumbing engineers I talk to who haven't really thought about it much would say, I don't know, at least 50% are going to be on. And the answer is 10 to 15. Both buildings. Why? Well, at any given hotel, aren't there likely to be people there from multiple time zones? So yeah, we all have to be at the meeting room at 8 o'clock in the morning, but if you're from the East Coast, you woke up earlier than I did, right? And so you're likely to take your shower at your time, go get breakfast at your time, and I'm likely to do it closer to the time of the meeting because I got in at midnight and I'm tired at this point in time. And so there's a lot less simultaneity, a lot more diversity than we would typically estimate, even under peaky conditions. Yeah, we all got to get on that bus, or we all got to be in the room, or we all got to go to the event. But we don't all shower or flush toilets at the same time. That's even true in houses, right? It's just the events where people tend to have things happen simultaneously are places where there's intermission. And that's not our dwellings.
Yeah.
And
So
this
here's
was
another question for you, Gary.
to instantaneous water heaters in homes that there'd be like range anxiety in cars. There would be not enough flow anxiety with instantaneous water heaters. You only could do 1 or 2, at most 2 showers at a time. So that was,
right.
And that was found not to be an issue.
Yes, and sometimes it's true it's an issue, like the house I was talking about, right? But that most of us don't live like that occupancy lived. That particular family had a home that acted like a small hotel. They had, visitors that might live with them for 6 months at a time, called grandparents, right? They built the house to do both at the same time. Well, but they didn't put the water heater in to do that right. They didn't design it right. If we understood the occupancy, we would have designed it differently in the first place. But most people don't have a problem with a water heater that's a tankless water heater that's got a capability of 5 gallons per minute of hot water, which is about what the 200,000 BTU unit will do for you. 4 to 5 gallons per minute at peak. The problem is at 4 to 5 gallons per minute, the pressure drop through the water heater is 20 to 25 PSI, and that's the problem that slows everything down and makes people unhappy. Not that it can't do it, it just can't do it very fast. Water won't flow well.
Mike, we're on the hour. Do you want to grab the last few questions, or if there are any, or?
Yeah, we can go another 15 minutes if we have to 1/4 the hour.
Yeah, we do have a few more questions, Gary. Here's a really interesting one. Came in from Kimberly. What time of year were the flow rates measured? And how sensitive to the season and the climate are the peak loads due to variables like differences in supply water temperatures or occupant behavior differences like more hot showers when it's cold, that sort of thing?
Great question. So the central water heating in all of these apartments had master mixing valves. And so the heating of the water was sort of happening off cycle of the use of the water. So it was heated higher than it needed to be for specific use. So it takes more energy to heat the water if it's colder to come in with, and you need a bit more hot in the mix in the winter than in the summer. And so this number will vary, but I'll go back and do the math, Kimberly, and I think it's going to go 20%, something like that. It's a great question. It does need to be accounted for. And I don't remember specifically when these numbers were taken. I'll go back and look. It's a great question. Thank you.
Another one from Drew. He says, well, why not just install flow control valves in existing systems and reduce water and sewer charges that way?
That won't change the water and sewer charges. They're based on the meter size. Consumption is consumption. The meter size has already been picked. The only question is, will they let you put in a smaller meter based on this data? And I don't know, maybe. It's a great question.
Rick had a question. Are there any issues unique to a heat pump water heater with an outdoor condenser and indoor indirect storage tank?
Not from the water heating, not from the water system sizing. There probably are from a heating issue sizing, but I don't see any obvious ones from the plumbing, just the water distribution sizing.
Okay. Steve wanted to know if you could talk a little bit more about the insulation, because you were talking about hot water pipe insulation, but can you talk a little bit more about the insulation on a hot water circulation loop that's like a 1/2 inch pipe and a 3/4 inch pipe?
Okay, well, yes, I can. Do we have a couple of days? Question is, what are you aiming for? The building codes, the energy codes say different things in different jurisdictions. And so if your code says you only need a minimum of 1/2 inch wall thickness everywhere, then your heat loss rate is based on the diameter of the pipe and the outer diameter of the pipe and pipe with insulation on it. So 3/4 looks like one. So it would be 1 3/4 outside diameter, and 1/2 inch looks like 1 1/2 inch diameter, right? Roughly speaking, outside diameter. So the heat loss between the two is different, but not all that different, right? Even though the pipe diameters are an order one off. And so some jurisdictions, like the Uniform Plumbing Code jurisdictions, say that the wall thickness of the pipe insulation shall be at least equal to the nominal diameter of the pipe. So 1/2 inch gets 1/2 inch, and 3/4 gets 3/4, 1 gets 1, etc., up to 2 inches. The IECC is commercial, is different than IRC residential for energy. And it says you have to have at least 1 inch wall thickness on everything up to 1 1/4, maybe 1.5 inch pipe. I forget the exact part of it. And then after that, it gets a bit bigger. And so each of those rules creates different heat loss rates. And so the rule I like best is the wall thickness equal to the nominal diameter of the pipe, or some proportioning related to that. Why? If you do the math, you will find that the heat loss per foot remains the same for all pipes insulated that way. It's off in the second decimal place, sometimes the first decimal place. So it's a really good basic rule of thumb. This one works. And so that's what I would prefer to see. But if you start out the way the rules are currently written, if you go from a 2 inch pipe that has 1 inch of wall thickness on it to a 1 inch pipe with 1 inch of wall thickness on it, you lose less heat because you have less outside diameter to lose the heat with. And so we should take advantage of that.
Okay. Last question here is from Drew. Not exactly on what we were just talking about, but he's curious as to why we couldn't make hot water, at least partially, from the waste heat of the refrigerator.
Well, it would have been easier to do in 1970 when we had really inefficient refrigerators.
Right.
A typical, let's assume that a modern refrigerator takes, I don't know, 600 kilowatt hours a year to run, which is probably in the right ballpark. Okay. And in 1970, well, that refrigerator didn't exist, but if it did exist, it would have taken more like 2,400 kilowatt hours a year to run. So a lot more energy. So virtually all of the energy that goes into the water, into the refrigerator, ends up as waste heat. And so you've got 600 kilowatt hours a year to work with. Do your best. It's just not a lot of energy.
Right.
Because remember, that's whole year, so it's 2 kilowatt hours a day. And it takes more than that to heat water. That's why we don't use waste heat room refrigerators much. However, if you're in a commercial kitchen and you've got lots of things going on, so extracting waste heat from that space is a really good one. And if you, I remember working on a project about 10 years ago that was a sort of a group home, and they had big refrigerator freezers downstairs, and they ducted the air from that space to the heat pump water heaters, which are sort of behind the wall in the mechanical room, and they sucked hot air out from the refrigerator space to make the heat needed for the heat pumps. That worked well, but that's an abnormal situation for most of us.
And typically, how much kilowatt an hour do we devote each day to heating hot water?
Yeah. I would guess it's, for resistance, it's probably 15.
Okay.
A heat pump would be 5, roughly speaking, for the same work.
Gotcha.
I'm doing numbers in my head that I haven't looked at in a while. I'm willing to go back and look at that and send you a note. We can figure out how to post the answer. So it just, there isn't much of a source of energy. I have another one of my friends who put his heat pump in his garage that had a window facing to the south and the west, and let the sun into the garage space, so it would warm up the garage, and it would warm up the air in the garage, and they could use that to help with water heating. They were going to have the heat gain anyway. They may as well extract the energy from it.
Right. Okay.
Cool.
Well, we don't have any other questions. So Gary, thank you so much for presenting this to us, sharing this knowledge, and I think as it was implied, if not expressly stated earlier, we hope that people are able to utilize this water demand calculator more, and that building officials get more comfortable with the data that it puts out and the results, and because this is really a big deal, and can't stress that enough.
So I'm going to make the offer that those who are wanting to go down this path, you should reach out to me. And I think that Mike and Sam, we need to develop a strategy to help people through the curve, and maybe do webinars with people who have done it and share what they learned so that others can follow the path. There will be resistance.
Sounds good, Gary. Even documenting case studies, how people went from less to more compact duct layouts, and examples of using right sizing plumbing would be great. So.
Yep. Yeah, we've pretty well done a good job of documenting the work in upstate New York. We presented it at the New York State Green Building Program earlier this year. Was well received. It works. But there will be pushback, always. It's change. It's normal.
Well, before Mike wraps up, big thank you from me as well for joining us today. I hate abusing friendships, but I'll do it. Hey, thanks so much for coming.
You bet. Bye-bye, everybody. I'm going to sign off.
Thank you to our audience for attending and asking wonderful questions, and also our sponsors, Mitsubishi Electric, Panasonic Healthy Indoor Living Solutions, Huber Engineered Woods, and Schneider Electric for their generous sponsorship of this webinar. Now, if you liked what you heard today, this is the kind of insight and knowledge that you can expect to get in the Housing 2.0 program. And you get to hang out with Sam and I. Well, I don't know if that's a selling point or not, but anyway, for more information and to register for the upcoming Q3 workshop series, which begins on September 2nd, please go to www.greenbuildermedia.com/housing-2.0. Our next webinar is going to take place on Tuesday, August the 3rd at 2 p.m. Eastern Time. We're going to be talking with Neil Friedberg about building and designing with resiliency in mind. That's going to be the first of 3 webinars that we're going to do in August. Until then, stay safe, stay cool, and take care.